Hello everybody, my name is Matteo Marini, I'm a PhD student from Sapienza University of Rome, and this talk will be about efficient detection of use-of-uninitialized memory errors while fuzzing. Now first of all, what are use-of-uninitialized memory or UUM errors? Well, let's take a look at this code that attempts to read 4 bytes from standard input and compare the first one with some magic value. If they match, it prints hello world. But what happens if nothing is read? What happens if the read function fails to read any byte? Well, in this case, A would be uninitialized, but it would still be compared with the magic value in the if statement, leading to a use-of-uninitialized memory error. These kind of errors are very difficult to debug, and they often cause non-deterministic behaviors, and they can have security related problems, and they are very difficult to detect without the use of specialized tools. To detect this kind of errors, the workflow is usually as follows. We first need to define a shadow memory, which is a memory region that contains the initialization status of other memory objects, as it is common to have a shadow memory with many other software sanitizers. Then this shadow memory is propagated throughout the execution, and it is checked on sensitive operations like pointer dereferentiation or conditional branches. If uninitialized data is used in sensitive operation, an error is raised. Now, why do we need these last two steps? So, why do we need to defer UUM error detection at sensitive operations? Can't we just raise an error if we are loading an initialized memory? Well, unfortunately, loading an initialized data is allowed as long as its content is not used in sensitive operations. Let's, for example, think at the case where we have a partially uninitialized buffer or an object that is only fully initialized depending on the context, and we want to copy it. Since to copy it we have to load it, then loading uninitialized memory has to be allowed. The state-of-the-art solution to detect this kind of errors is called memory sanitizer, or MSan for short. It is a compile-time solution, and it is very accurate thanks to the fact that it has access to the full knowledge about the program at compile time, and it is also fuzzing compatible with an acceptable slowdown in the range of 2 to 3x. On the other hand, MSan requires recompilation of the software, and all the code in the user space stack during the execution has to be instrumented with MSan, including the libraries. This makes MSan, while fuzzing compatible, still not very fuzzing friendly. Because of this, the famous OSFuzz project had to disable memory sanitizer for all projects a few years ago because of an update to the operating system version in the backend. And to this day, still more than half of C and C++ projects in OSFuzz cannot use, do not use MSan. Further, MSan is only available for LLVM. The workflow for MSan is as follows in the program we saw before. So at first, all the memory for both buff and A is going to be uninitialized, and we have no way in knowing what's the content of these two variables right now. Then let's assume that the read function is able to read 2 bytes from standard in, so the first 2 bytes of buff are now initialized to some value, and the shadow memory reflects the initialization status. Then the first byte of buff is copied into A, which means that now also A is initialized, and then when there is the comparison, MSan will check A's shadow, which is initialized, and so the execution can continue without raising any error. Now, since MSan has all these issues with recompilation and with requiring all the libraries to be instrumented, you may wonder if we can detect this kind of issues at the binary level. And the answer is that yes, we can do that. We can do UUM error detection at the binary level, and the workflow is very similar to MSan's, but much more instrumentation is needed. for this kind of solution. So this kind of solution are more generic in the type of software they can instrument. They require no recompilation, and they can also target closed source software. On the other hand, they are much slower. Their slowdown is in the range of 10 to 20x, and this is because shadow propagation is much harder at the binary level, and they have no fuzzing compatibility, which means that we are missing bugs for closed source software, and we don't have a more generic solution for when MSan cannot be deployed. To tackle this issue, we propose a new approach called QMSan. QMSan is a binary-based multi-layered solution to detect use-of-uninitialized-memory errors. It is based on the QEMU emulator, and it is fuzzing compatible, in particular with it has compatibility with the state-of-the-art AFL++ fuzzing solution. QMSan has three main components. The first one is an accurate detector, which is similar to existing UUM binary errors, UUM errors detection for binary software like Valgreen's memcheck or Dr. Memory. It is very accurate, but it is also very slow. Then it features a runtime module that supports UUM detection with shadow memory management. And lastly, it has an opportunistic detector, which is a new UUM error detector, which is very fast but also very inaccurate. This opportunistic detector is based on the key intuition that most loads of uninitialized memory are safe. Most of them come, for example, from optimization, from low-level tricks that do not really result in use of uninitialized memory errors. So we don't need to check them every time. We can just check them once and then remember in a fuzzing run whether they are safe or not for the future executions that won't need to check them. So the opportunistic detection works as follows. It only checks memory accesses, both load and store operations, without performing shadow propagation. When we detect a write operation, then we initialize the shadow of the target memory we are writing on. When, on the other hand, we have a read, we check the shadow of the target memory we are reading from. If it is initialized, then we can go on with the execution because no use of uninitialized memory can arise from loading initialized memory. When we detect that we are reading uninitialized memory, then we have a violation. And when a violation occurs, we can have two cases. The first one is that this violation is known. We have already seen it, we have already tested it, and we know that it is safe, so we can keep executing. Otherwise, if this violation is not known, then we use propagation, we use shadow propagation, so a slower instrumentation to check this violation and remember it for next time, so that the next time we find this violation, we won't need to use expensive instrumentation again. The workflow of QMSan is as follows. We run the program under testing in the opportunistic detector. Then, whenever we detect a violation, which is a load of uninitialized memory, we check it in an ignore list to see if this violation is known and safe. If it is, we can resume the execution as if nothing happened. Otherwise, we have to check this new violation with the accurate detector, which means that we are going to replay the execution with the accurate detector, which will tell us if this was a false positive or not. If this was a false positive, we add the violation back to the ignore list and we resume with the fuzzing. Otherwise, if this was not a false positive, we raise an error because we successfully detected a use of uninitialized memory error. The key idea behind this design is that we are going to use the opportunistic detector in the vast majority of the runs, which is very fast, and only use the accurate detector in a few runs to detect the true errors, the true use of uninitialized memory errors. Now, this setup needs an ignore list to remember what violations are safe to avoid executing the accurate detector too many times. It is very crucial that we identify successfully every violation because if we use too shallow properties, we may end up having false negatives. QMSan uses three properties to identify violations. The first one is the instructions, the address of the instruction that triggered the violation. This by itself is able to uniquely identify the instruction, but the same instruction that can load uninitialized memory may sometimes result in a use of uninitialized memory, while other times not doing that, depending on the context. So we augment this our policy with two more properties. The first one is spatial locality, where we take into account the calling context when the violation happens. Then the third one is temporal locality, in which we take into account the sequence of violations. We find these three properties to characterize well enough the violations to not have false positive in false negatives, sorry, in practice, which we did not observe during our evaluation. About the evaluation, we evaluated QMSan for bug finding capability on a dataset of 9 closed source binaries from common target for binary fuzzing papers, and 10 open source programs from OSFADs that we detected as the 10 programs with the highest number of security related bugs in the last 2 years on OSFADs. We made 3 runs of 72 hours, and we ended up detecting 27 bugs in the latest versions of the closed source software and 17 bugs in the latest versions of the OSFADs projects. For the performance, we had to change dataset because we had to use programs that were compatible with MSan, unlike the 10 OSFADs projects we used for bug finding capabilities. And we have chosen 8 programs from the Google Fuzzer test set. We detected a final slowdown on 1.51x over QEMU, 1.55x over compile time QMSan, and a total slowdown of 3.75 over AFL compile time instrumentation. So in the end, we can say that detecting use-of-uninitialized memory errors is a challenging task that tends to either introduce high slowdown or have compatibility issues. We presented a new design that increases compatibility with software while still incurring in a reasonable slowdown. We detected 44 new bugs, for which 4 CV IDs were issued, and we have a slowdown of 1.51 x over the binary fuzzing baseline of QEMU. This is the link where you can find the source code of QMSan as well as all the data, the relevant data from our evaluation, also for reproducibility. Thank you.